I said in the last snippet that there was a possibility that this one would be the last. I've looked it over. Maybe I'll include short snippets on spontaneous reaction and electrochemistry. But otherwise, this is the last of the main ones. This is the last of acid base. Now, salts produce cations and anions when they're dissolved in water. And I show the illustrations of this with examples. Sodium chloride dissolves to form sodium ions and chlorine ions, potassium carbonate, aluminum nitrate. This shows the ions. Generally, column 1 and 2 elements and column 7 act as spectators in reactions to water. The exceptions are chlorine ions, bromine ions, iodine ions, nitrate, chlorate, and sulfate. Now, which is which for this? Ammonium ion is acidic. Zinc 2+ ion is acidic. Potassium is a spectator. Sodium, spectator. Iodine, spectator. Sometimes it's acidic. Nitrate is a spectator most of the time. Occasionally it's acidic. The chloride ion, spectator, occasionally acidic. The phosphate ion is always basic. Now, from the last lecture, again, I'm making one of my transferal errors. I said the ammonium plus Ka was 5.6 times 10 to the minus 10th, and that's correct. The pKa of the negative log of 10, 5.6 times 10 to the minus 10th is equal to 9.25. For some reason, I don't know, brain switched off. This was 5.6 times 10 to the minus 7th, and that was 7.25. That's totally incorrect. So please correct it from the last. So I purposely circled this so I wouldn't fail to mention it. Okay, let's go back to the top up here. If the constant of the base is greater than the constant of the acid, then you have a basic salt. Now what you have is ammonium chloride here, where the ammonium ion is 5.6 times 10 to the minus 10th, and the chloride ion is 3.6 times 10 to the minus 7th. Thus, the pH is 8.4, and it's slightly basic. Over here, when the Ka is greater than the Kb. Now, you ask me, where in the heck am I pulling these out of my hat? No, this is stuff that's in the charts in the back of the books. Remember I said get old books that have these charts in them so you don't have to look them up online each time. It's nice to have a kind of, I disagree with the way some of these modern texts are written, in that they don't have everything consolidated in one location. Yes, it's cheaper to produce, but it also is not as easily referenced. So it's a disagreement among colleagues. All right, back to the top here. The Ka is greater than the Kb, and that means the ammonium fluoride, the Ka of the ammonium is 5.6 times 10 to the minus 10th, same as it is over here. The Kbf is 1.4 times 10 to the minus 11th. Thus, the pH is 6.2, and it's slightly acidic. So, okay, now amphoterics act both ways. Now, that sounds weird, but it's true. You got the bicarbonate ion plus water can act as a H3O ion plus a carbonate ion, and the Ka is 4.7 times 10 to the minus 11th, which you can understand is basic. The bicarbonate ion plus water also can act as a H2CO3, which is carbonic acid, and the hydroxide ion. The Kb is 3.2 times 10 to the minus 6th, Is it 2.2? Let me look at my cheat sheet here. Times 10 to the minus 6, which is slightly acidic. Okay, the simplest way to find the Ka is to dissolve the weak acid in a known quantity of water. So if you're going to take your acid and we'll say dissolve 3.6 grams per liter and divided by the molecular weight of the acid, which is 180.15, you come up with 0.02 molar. That's just making a solution. You've done that previously. And you're given in the problem that the K equivalent or the equilibrium constant for the hydrogen ion is 10 to the negative second. And that, when you do the log function of it, comes out to 2.5 times 10 to the minus third molar. So that's what you start as your basis. So when you begin the whole situation, you got the acid is 0.02 moles. You made it that way. Now, when you put it in water, it starts to dissociate. When it does, the concentration of the acid that you began with loses 0.0025 moles to the two components, the conjugates. Thus, at the end of this, you got 0.0175 and 0.0025 and 0.0025 of those components. And to find the Ka of this, you take the 2.5 times 10 to the minus third, which is what that is, divided by 0.0175, and you come up with 3.6 times 10 to the minus fourth. And that gives you your Ka value. That's the easiest way to do it. Now, this only works with solid acids, obviously, because you can weigh them easily. And remember, volumetric expression is really tricky. You got to have really fine instruments, and you got to have a pretty good eye. Mass relationships much easier to work with because your metric scales are to the thousandth of a gram quite routinely. Now, back in the old days when I was chiseling notes on rock, you had a double pan balance, and you had to be able to get your masses by adding small quantities of known grams to the substance you wish to start with. And it was really tricky. Now, later on, of course, we got dilograms. Probably, I don't think I was around long enough to get dilograms, but the dilograms allowed you to just dial it to where it balanced. And that was much easier to use. But in this situation here, you always want to use the measurable solid acid, because you know the molecular weight of it. All you got to do is add it up, and you can make a solution to whatever molarity you want. And then when you throw it in water, you know it dissociates equally amongst the two components, and that gives you X, and X, which is X squared, and you can go from there. Now, some of the time it'll be given to you like it is here. The K equivalent is given as 10 to the minus third. So that's sometimes given to you in the problem, which makes it even easier. Now, percent of ionization is found by changing the pH to the concentration, which means 2.5 times 10 to the minus third over 0.02 is equal to about 12% ionization. Now, 12% ionization is a ton. especially for a weak acid. They're often less than one. And less than one ionization indicates a very weak acid. This one is a very strong weak acid. If that's not a double negative, I don't know what it is. So anyway, that gives you an introduction. Now, this may be the last one, but I'm kind of leaning towards variant equilibrium and electrochemistry, which I'll provide one snippet of each. And that will give you a much broader survey course than I had intended at the beginning. But this is kind of going along, and hopefully you're able to full screen these board illustrations that I have. They're readable to me, and I'm half blind, half deaf, which happens to us old folks. So you younger, more optically efficient folks should be able to full screen that and blow it up to where you can readily see it and use it as a reference. Okay.